Hello, and welcome to Managing Data in a Distributed Environment. Your next project will ultimately be seen on a desktop in Tokyo, a tablet in London, a mobile phone in Seattle, and even on wearables and standard household items in Prague, Dubai, Dublin, Houston, and elsewhere. Or maybe you'll deploy to dozens of stores all across the nation and need to track in near real time the state of inventory and flow of operations across widely separated locations with varying levels of connectivity. As the number of users, both human and machine, expand, the need to have multiple systems distributed throughout the globe is the new standard for a successful application. There are three keys you need to open up your distributed system to high performance, low complexity, and reduced latency. Today, RavenDB CEO Oren Eini will demonstrate how to manage your data in the ideal distributed environment, making every node in your system its own full-service data center to best serve each user coming at you from every corner of the world. If you have any questions, at any time, click the Q&A button at the bottom of your screen, and Oren will be happy to answer them at the end of the presentation. Enjoy, and here's Oren.
Hi, everyone. Today we're talking about distributed environment, and we are very likely doing that in a highly distributed environment of our own. The coronavirus has forced pretty much everyone to work from home. And that is, for some of us, it's okay, part of life. For some of us, it's, oh wow, a whole new experience. For RavenDB, we've been dealing with distributed environments of various kinds for a very long time. And I wanted to talk about some of the core features that we have available in this environment. The first thing that I want to discuss, however, is some logistics. We are typically doing this sort of webinar every 4 to 6 weeks. Because of the coronavirus, we have decided to move it to every week. I would truly appreciate if you could send us either in email or in the chat right now any ideas and requests you have for webinar topics, stuff you would like me to cover, RavenDB architecture, whatever you want. Please send them over, and we'll be very happy to tackle them in due course. And now let's talk about RavenDB and distributed environment. So the first thing that we need to understand is that RavenDB from the get-go has been distributed. What does it mean? It means that we may have multiple nodes in the system. But RavenDB actually takes data distribution to several new levels, because in RavenDB you have distribution at the database layer, at the cluster level, multiple clusters, widely distributed gossip hierarchies, ETL, and a whole bunch of other stuff. Some of this probably doesn't make any sort of sense to you, which is fine. That's why I'm here. So let's start by showing you the lay of the land. What I have here is RavenDB Cloud. And you can see that I have 3 separate clusters running. This guy is running AWS in Paris. This guy running Azure somewhere in West Europe. And I also have an instance running in North Virginia. Important to understand about all of this, those are 3 separate clusters. This one has 3 nodes, so it's a fully capable cluster, and those 2 are just single nodes. I'm simulating an environment in which the cloud is the production instance, and I have 2 of those instances that are standalone RavenDB clusters. For example, one running a shop, for example, something that you run on your own tablet, those sort of things. Now, let's talk about this one, because this is the classic cluster running on 3 separate nodes. Because we're running in the cloud in AWS, each one of them is running on its own availability zone. You can run RavenDB on-premise as well, obviously, and there are, in this case, these 2 guys, the EU and the Virginia one, are simulating just that scenario. So remember that the white-looking thing, this thing, the white theme, the light theme, is the cloud instance. You can see it here. We have 3 such nodes. And let's look at the cluster itself. You can see that I have a cluster composed of 3 nodes, and the first thing to understand is what is the cluster view for RavenDB. And from the cluster point of view, I have multiple nodes, all of them are working together. And there is a simple rule, majority rule. Multiple nodes running together, and any two of them gets to decide what's going on. For example, let's go here and consider what's going to happen if there is some sort of a failure. I'm going to look at the cluster view, and then I'm going to introduce a failure into the system. I'm basically going to force a restart of node A. In a couple of seconds, this one is going to go away. And here we go, so connection loss. And let's see what happened. Node B and C had a discussion. We used to have node A used to be the leader, and node B and C are now deciding who is going to be the new leader. We can also look at that from, and they seem to have been stabilized. Sometimes it takes a little while to stabilize after such a case. The interesting thing about this is that from the point of view of my application, and A is back up. Sorry, I really have to fix that. The restart cycle for RavenDB is too short, so this demo goes away too quickly. But what's important is that even if this happened, a node went away, from the point of view of my application that is using the database, then everything is still running normally and operates with no issue. The other thing to remember is that not much actually goes through the cluster. The RavenDB cluster is used to manage the metadata of the entire thing. What do I mean by that? It means that I need to talk about databases, indexing, cluster-wide task, monitoring of the system, those sorts of things. Aside from cluster-wide transactions, the cluster doesn't actually manage your data. It manages the database that holds your data. And that actually leads us to a very interesting observation, because we have the notion of database groups. Now, what is a database group? You can see here two models. Here I have a fully replicated system. Every database resides on every other database in the system, on every node in the system. And here I have a partial model where we have 5 nodes in the cluster, and helpless, for example, is only on 2 of them, only on 3 of them. And ledger is here, here, and here, but not here or here. So the idea here is that a database group is composed of multiple instances of a particular database. Here is a database group that contains a single instance. Here's a database group that contains 3 of them. Now, let's talk about the data. Here, this is a database that resides on 3 nodes, and it has no data. I'm going to write some data here. It's not really that interesting. And it will show up on all of the other nodes. This is fairly typical. It's fairly typical. I modify data in one node, it shows in the others. The important thing to understand here is that I'm using the multi-primary model. Now, what is this multi-primary model? It means that I can make a write to multiple databases at the same time. Let's look at what I'm doing here. You can see here that I did something interesting. I'm writing to node A, car2, and node C, car2. And I'm writing 2 different values to each one of them. And I'm doing that in a asynchronous manner. This is remote, so it's likely hit very close to one another. Let's look at what we have in the database. And let's make sure. Using the demo. It should have worked. Okay, For some reason it didn't. I don't want to try to debug that, but what I was trying to show you is that, and that's really annoying. Let me try doing it like this. Maybe it will be easier. Okay. Oh, it did not start. Okay, let's try it this way. I'm going to write all of them together. And hopefully that would make things easier. Here we go. Apparently my PowerShell foo is not very good. Now what you can see is that I brought them to different nodes, but all of them are going to end up with the same value. Even if I brought them, but what happened if I wrote them in the exact same instant? What would happen then? It's actually very hard, and apparently I failed to do the PowerShell, the appropriate PowerShell foo in order to demonstrate that. So let's talk about something simple. Let's go to node A. And here you can see you have cart 1. Notice that we have 2 milk and 1 bread. In node B, we have 1 milk and 2 eggs. I've set it up so A and B would replicate to database C. And here we can see that we have 1 milk and 2 eggs. Where is the bread? Let's say that I'm going to go here and say that, I have 3 bread. And here we go. What happened? What happened to the eggs? And again, going here. So what we're actually simulating here is something quite interesting. In a few seconds, we're going to see the rotary eggs. So basically, we have an interesting scenario. A and B are replicating to C. And whoever wrote last is going to win. Effectively, what I'm trying to simulate here are 2 concurrent writes to different nodes in the cluster and to show you what happened when they arrived at each other. And what happened is that we resolved that. We identified the conflict, and we need some way to fix that. Actually, we haven't lost any data. We can go here and see here the old data. And because RavenDB uses this model, then we have to also deal with the fact when I'm talking about uses this model, I'm talking about uses the multi-primary model. We have to deal with the fact that a document can be modified in multiple locations at the same time completely independently. Now you ask, well, why are you doing that? Why not forward that to the primary node? And the answer for that is very simple. What happens if I don't have a primary node? What happens if, as far as the network is concerned, the connection between node A and node C has been disconnected? This leads to the CAP theorem. I don't want to go into that. It's an interesting topic, but it has been covered extensively as well. I just want to talk about how RavenDB handles that. RavenDB handles that by always accepting a write. And when necessary, you're going to get conflicts and you need to resolve them. We'll see exactly how it works in a bit. It's interesting to understand that from the point of view of the database group, the cluster treated as a set of independent items that all work together. They have shared responsibility. The cluster may decide to change it dynamically. For example, I can go here. Let's look at catalog is a good example. You can see that it has a backup. And let's say that, I don't want to know that anymore. So the responsibility moved to another node. Notice that here I have allowed dynamic database distribution. If node B or C were down for a significant amount of time, then the database would say, you know what? I can't live with just one copy of the data. I need another. So it would automatically introduce a new node into the system. that node would pull up the data from another node, and eventually it will accept new responsibility and be promoted to a full member in the database group. Now, there are other interesting things that happen here. The first thing that we have to understand about distributed environment is that failure is something that happens. Failure is something that happens all the time. And it's interesting how RavenDB handles failures. We have collaborations between clients and servers to handle failures in an optimal fashion. What do you mean by that? The first thing that a client does when it connects to RavenDB is ask the RavenDB instance, tell me what is your topology? What databases, what nodes is this database resides on? And in this case, what we will tell a node that wants about the catalog, you can talk to node C and B. There is also some data on node A, but it's not ready yet, which is fine. Now, the cluster is free to change the order of the nodes in the system. And clients are going to use the list of nodes in the database group topology as a hint of who they should talk to. And they always want to talk to the first item in the first node in the list. However, if this node is down or inaccessible to this client, they're going to fail over to the next one in the list. Now, what does it mean? It means that the client, independently of the cluster, independently of the servers, can decide how to fail over. If a node fail over, the client gets an error and immediately retry on another node. The server at the same time, the cluster at the same time, monitor its own state and decide who should be the primary node at any time. So we attempt to use a single node, but we don't have to. It's an optimization more than anything else. You can also define how the client should behave. It should always use the first node in the list, or it should use round robin, or it should find the fastest node that it has to work with. Now, notice that for some reason we're not seeing this join as quickly as I expected. Let's go here and see what's going on. We have everything here. It might be just waiting for something, but the data and everything is already here. And as soon as this is up, then we'll have full capability. This will probably move back here, and the database group would be fine again with all nodes. Remember, because of this can happen dynamically. So what does this mean? It means that clients, I mentioned that clients and servers are cooperating here. Whenever the database group topology changes, the client will be notified. So under normal circumstances, I always have the latest topology, so I can always find one of the appropriate nodes. Now, I started talking about conflicts, and we demoed the conflict. Now, conflicts are rare, but at the same time, they happen all the time, which is strange. It's strange because in our business, given current CPU clock speeds, 1 in a million chance is happen 100 times a second, 300 times a second. So we have to deal with that. RavenDB automatically resolve conflict. It's the cheapest and easiest way to handle that. Let's go and look at node C. And let's look at how it works. We have automatically that, so this is what happened. We use basically the latest version, whatever that is. And we are guaranteed that regardless of how it works, latest version is going to be consistent across all of the nodes in the cluster. Now, let's see what's going to happen now. I'm going to update this to 4. And now you can see that I got a conflict. I disable the automatic resolution. So now I have a conflict. Here I have 1, 3, 1 milk, 3 eggs, 1 milk, 4 eggs. And the reason for, and I have a conflict, I'm going to resolve that to something. You can see here that I have, it's similar to how you resolve conflicts in source control. And I resolve it to here. And now we're good. Pretty much no one ever used this format, manual conflict resolution. Literally, the only reason it is usually used is to demo conflicts, to show how it works. At the same time, consider the fact that I'm going to go here, not catalog, going to go here and add another bread to my basket. And here, I have again a conflict. Now I can go and enable this again. This will resolve it to the latest version. But I'm now missing the eggs. Probably not what I want to do. The nice thing about conflicts is that 95% of the time, you do want to use the latest version possible. Why is that? Because in most cases, you don't care about conflicts. For things like shopping cart, however, things that where you actually expect to have multiple concurrent updates, and it is important to have all of them, you need something else. Now, just to clarify, why don't I care about concurrent updates to a user's record? Because if the user update two different fields at the same time, probably the latest one wins anyway. Now, I'm going to go ahead and define on cards the following script. And basically, we have docs, array of conflicted items, and a whole bunch of other stuff. But the basic idea is that I take one of the docs here, that's the final version. I iterate on all of the other documents and then say, okay, let's merge this guy. It would be easier if I look at it this way. So for each one of the things in the current cart, try to find it in the final version. If there is no match, add it to the items. If there is match, set it to the maximum value. Going to edit and save. Now let's say that I have 5 here and 71 here. This is because in Corona times, you need all the milks that you wanted. Now let's see what's going to happen now. Here is milk, bread, and eggs. So our code, our policy for resolving the conflict has merged the whole thing. I can now notice that in order to build this demo, I had to set up one-way replication. I did it using this mode, from B to C, and from A to C. On the other hand, node C is not replicated to anywhere. What you would typically do, you would apply such policies somewhere where you have multiple nodes in the system. Something like this. And then right here, one of them would resolve it and send the updates to the rest of the system, and it would resolve everything in this fashion. Okay. As I mentioned, this is not an error. It used to be the case in before version 4 of RavenDB that conflicts were treated as an error. You would have to catch an exception. And we changed that behavior. We changed that behavior because it is rare enough that people don't write any error handling code for that. And then you have some network hiccup and you have a conflict, and then the whole system dies. That's why by default we have a default handling that will allow you to write your own policies. And if you don't do anything, this means you don't care, then you please proceed with the data. And if you need to, you can always go and look at the conflict revisions so you don't lose any data because of that. Now, let's talk about something interesting. We mentioned that inside a particular database group, I have automatic failover, client and server, and all of that. Now, that works great as long as that's something that I want. Let's talk about a case where I have multiple data centers. One way of setting up RavenDB in the case of multiple data centers and geo-distributed environment is to have a single cluster that is geo-distributed. And that works. That works perfectly fine. However, this tends to be something that you generally don't want to do. Why is that? Let's say that I have New York and London clusters. And I have worker nodes in London that are talking to my London clusters. If all of the nodes in London have failed, I don't want the London worker to go to New York to get the data. That's probably going to be a killer to my application. And I would refer you to the GitHub outage of October 2018. They had an outage that caused them to reroute database queries from the East Coast to the West Coast of the United States. So we have a web worker role in the East Coast, and it now needs to go and make a database query to the West Coast. It doesn't sound like something momentous. It's just, just go to the other data center. It's probably going over private link. How bad can it be? Well, the answer here is that it was bad enough to take them down for 24 hours. And what happened was very simple. Each request under the cover makes multiple queries to the database. Let's say 10. When your nodes are sitting here and your cluster is sitting here and your worker roles are sitting here and you make 10 queries to the database, the latency of each request is about 1 to 2 milliseconds. So the overall cost that you have here is going to be 10 to 20 milliseconds wasted on latency of the network. But in the case of moving that from a same data center to East Coast to West Coast, now you have 30 to 60 milliseconds of delay just for the network. So now something that could be completed safely within a time budget of 100, 200 milliseconds now may take 300 to 600 milliseconds. And this is assuming that you have just 10 queries per request, which is not a safe assumption to make. The latency was high enough that they started getting timeout error across the board. So you tend to not want to fail over across the Atlantic or fail over in a distributed environment. You tend to want to, I want if this can talk to the local database, I would rather route the traffic to New York instead of handling that in London, because it's actually going to be cheaper to do all of the computation here and send it back as a single operation. Now, I still want to share the data. So in order to handle that, this is where we use external replication. The idea here, The idea here is simple. Just like in this case, where I push data from node A to node C, this is what I'm doing. In this case, node A happens to run on the same location, but I can also run it on different clusters, and it works. And that creates a shared data across multiple clusters. And now we run into multi-primary mode globally, because I have multi-primaries here in London and I have multi-primaries in New York. Now, the nodes in London will try to select one of these as the primary and one of these as the local primary. But it is absolutely guaranteed that I'm going to have writes here and here, which is fine. RavenDB is just going to handle that. The data is going to be shared. If there are any conflict, we'll resolve them, and everyone would move on. However, we need to talk about something quite interesting. How do you handle globally unique identifiers? GUIDs, but don't use GUIDs. Now, one way of handling, what's the issue? The issue is what happens if I need to create a new item in London and New York at the same time, or roughly the same time. I'm going to create a new to-do item. If I call it to-do item 5, then it's pretty much guaranteed that I'm going to see it in here at the same time, and I'm going to get a needless conflict. Probably not what I want. So I need some way to generate IDs in a unique fashion across the board. One way of doing that would be to use GUIDs, because, well, that's what they are for. They're globally unique identifiers. The problem with GUIDs is that they are not really human-friendly. Let me show you why. Here is a document. I can be fairly certain that I'm going to do the same thing. Sorry, see? I'm going to do the same thing on node B. I'm not going to get a conflict on the IDs. However, try reading something like this over the phone, or looking at on, or searching for that in the logs. So any of 100 things that we're doing on a fairly constant basis. By default, RavenDB uses some form of numeric identifiers. We can do it like this. And it's very easy for you to say 39C. And that's reasonable and memorable. Notice, by the way, that it's perfectly fine to have 39C and 39A. And this is the way inside a single cluster that we handle potentially the creation of new IDs across the board. With multiple clusters, we can't easily do that. The typical way to handle that would be to prefix or postfix each ID with London or New York to make the value unique globally, and let RavenDB handle the uniqueness of the value inside a particular cluster. Okay. Now, let's talk about data distribution. The scenario that we have in mind is simple. What you can see here is that I have a product catalog with some products. I have Virginia and EU instances. I want to get the product catalog in all of them. And the question is, how does it work? Now, in this case, there are simple ways of handling that. I can go here and define external replication. And it says, okay, one for Virginia, one for EU. It will work. The problem with doing that is that if I want to add a new instance, I have to go and update this catalog. And that kind of sucks. Because in some cases, I want to have lots of new instances. So in order to handle this, I'm going to say something like this. I'm going to use pool replication. What does it mean? Here we go. You can see here, I have this very simple setup. I'm going to say, okay, I'm going to set up a replication hub, call it publish catalog, and set up some security, which doesn't matter for us, and what this does is create an endpoint. This endpoint is now available for clients to come in and pull the data. On Virginia's side of things, I'm going to define the pull application sync. Let me just define it from scratch. If you notice here, I have the ability to say export configuration. So here I'm going to define a sync, pull the import, And apparently in this case, this is already done. So let's do it there. Okay. It would be easier for me to not deal with this, so let's just delete this. And now I define that. This is pretty much all you need to do. And now this node would go and pull the data from this node. I can add new items to the system without having to do anything, without having to go and modify the cloud. So deployment of more items in the edge is trivial. Now, you might have noticed something annoying. I have a typo here. Let's fix it and see what happens. In Virginia, I can see that it hasn't been updated yet. In the EU, it's already updated. And here we go. So this is interesting. This is interesting because we see different latencies. But anyway, within a second or two of me doing that, I can see that the data is updated globally. Something to understand about this sort of replication. This is meant for typically where you need to deploy many such instances. If you have one or two user external applications, use pool application, it doesn't matter. If you have a few dozens, then pool application is the way to go. And this creates the hub and spoke model, where you have one cluster, typically the cloud or central HQ, those sort of things, where you find your data, and you push data from it. Now, remember that we always have to take into account the issue of failures. What happens if I can't get the data out? What happens if I'm looking here at the system, and probably not A. Sorry, I'm trying to figure out where. No, so let's look at not B. So here we go. Here is the Virginia connected to this guy. And the interesting thing here is that I may have many such items here, pulling data all the time. If EU is unable to get the data, then it has the local copy, and it proceeds to operate on that without any issues. By the way, I want to apologize for the dogs, coronavirus and everything. I'm sure that you've all heard dogs, cats, pets of various kinds, as well as any number of children in online meetings recently. Again, I apologize, and I hope that we'll go over this thing and we can go back to doing webinars out of our really great office that unfortunately doesn't have any dogs in it. Anyway, so the idea here, catalog now in EU or catalog in Virginia, still EU, here we go, Virginia. Catalog in Virginia doesn't have to wait, doesn't need to work with anything else. You can work on top of your local data. And that's really good for partially connected systems. If you're running a laptop, tablet, if you have a system that is running inside the car or those sorts of things. We actually have apparently quite a lot of users who are actually using these features quite extensively. For example, you may be running this in each store that you have, and you don't want to take the system down if the store lost connectivity. So one side of this is data distribution. Now let's talk about something that is almost more interesting. And this is the idea of data aggregation. Let's go and look at orders. Orders here has some data, and in particular, it has a whole bunch of orders. This is a sample data that we have. I want to do product recommendations, and I want to do that Interesting. I can see that, okay, Pavlova was purchased with nothing else. Not really that interesting. But this and this are purchased together. That's a good hint that next time that someone purchases this button, they want also pasties. Okay, that's good. That's interesting. Now, I want to do something about that. Now, here I have something quite interesting. I have a MapReduce index. I'm actually going to have a webinar, I think next week, that talks extensively about data modeling and indexes and all of the cool things that you can do with them. But the basic idea is that what this does, it gives me product recommendations. Let's see how it looks like. Here is for this product, this one was sold the most. And that's interesting. That's really interesting from our perspective. But you know what? This is for this local shop. And if we go to orders here, we can see that we have the same index and effectively the same results, because in this case, the data is identical across the board, etc. So that's interesting, but it doesn't really help me because this is local to the current shop. Now, something to notice that the storage is different. Why is that? Because the storage comes from this document. I'm loading that during the index. I'm using that to globally uniquify the results. Now, here's a problem that I have. So far, I managed to pull data from the cloud using pull application. Now I want to send it out, but I don't want to send all of my data because all of the cloud doesn't need everything. I wanted to send just some of the data. This is why I have this thing. I set it up in the EU. This is ETL. And the ETL says something like that. Send the product recommendation collection. And where did I get this collection? This index here has an output with these results to collection. So the output of this index gets written here. And then I can use this ETL task to push it to the recommendation database in the cloud. Let's go here and look at the recommendations. And now we can see that we have data, but we only have data from the EU. This is because on the Virginia side of things, I didn't set up anything. Now, here I'm going to run into a problem, or somewhat of a problem. Let's see why. Let's set up ETL. And this is pretty much all I need to do. Now, oh, I have a problem. Why is that? I'm trying to connect to the cloud. The cloud doesn't know about me. Not anyone can go into my production server and write data in it. So I have to do something else. Let's see what I got to do. I got to tell the cloud about me. So I'm going to go to certificates and pull my own cluster certificate, this guy. And then in the cloud, I'm going to go to certificates, upload client certificate, and this is Virginia master, and I'm going to give it access to recommendation database. And now let's try it again. And now everything is good. So now I set up an ETL to push my data from the EU and Virginia to this database. And now I have more data here. Yes, this is from Virginia. Now, here, I'm doing MapReduce on the data again. This time creating global recommendations. Now you can see here is this. It is sold in many, many locations. Now, I want to show you something really, really cool. I'm going to go to Virginia. And I don't have product 11 here. So let's edit. I save it here. Now, remember that it was purchased 76 times. And now it's 77. Think what I just did. I made a local write in Virginia. This data was added to the database. This index picked it up, generated a new value for product 11A, and wrote it to a document here. It's probably this guy, or whatever. And we wrote it here. Here is the guy, 39 in this case, because this is local to Virginia. And then the ETL task picked it up and shipped it here, somewhere here. And then this picked up the local changes and gave us the total value across the board. Now, this sounds like a small thing, but it isn't. It's not a small thing because think about all of the things that I just was saved from having to do. I don't have to manage synchronization, I don't have to manage anything. I have to define the data flow between locations, that's it. If the local node is unable to connect to the cloud, it operates normally. It will send those details to the cloud later on. I also define the ETL process live in front of you to show you how it works. With security, with everything, that's how complex it is. And it's reliable and robust, and things can fail, and it will continue working and get you the results that you want. And now, if I want to add more locations, I deploy this guy. I deploy another one like Virginia. For the pull replication in the catalog, I have to do nothing. To allow a location to push updates to my database, I have to explicitly allow it, which makes sense. But now I have global recommendations for everything, and that works. You can also use the ETL for another use case. Let's say that in this case, this is actually a development license. Let's say that I want to deal with some data. And in production, I have this. So I have the Norton database, which is the sample data that I have. And I want to be able to push some of this data to here. How does it work? I can't push all the data. I have secret stuff there. I can use the ETL process to manage that. And again, in order to handle that safely, I need to set up security properly. So now from the cluster to Virginia, I'm going to add client certificate for and allow it to go to Northwind. And here we go. So now I'm going to set up ETL. And sorry, on database. Northwind dev. Except for employees, I'm going to add all of them. So push all of these, no, not employees, not employees. Great. For employees, where I have apparently some secret information, and I'm modifying the shape of the data that goes out. Now, I'm going to go here, and here is the categories with all of the data that they want. By the way, also including things like attachments on the data. But in the employees case, I don't have address, and the last name has been redacted. This is also very useful in order to handle development scenarios. I already spoke about using ETL for microservices and data distribution in other webinars, so I'm not going to go over that as well. We have a question now, I think, is the time for questions. So we have one from Richard Norman. In the ETL scenario, which is very cool, by the way, I agree. How chatty it is, or is there a lot if there are a lot of writes in lots of location? Will it load the servers? So in the ETL scenario, and in this case, we're talking about from orders here. So I don't know how chatty it is. Let's find out. Let's look at Traffic Watch. And I'm not sure which node it's going to write to. So I'm basically going to go to Traffic Watch in everything. And now in here in Virginia, let's go and update an order. Not in here, not in here, and here we go. So what we can see here is, okay, this is replication, it doesn't matter. Oh, it isn't change enough. Let's do, so if the data didn't change, we're not going to really do anything with it. Let's add another one like this. Here we go. So now you can see those are everything that changed within that batch. And it seems strange. Why do I have so many changes? Well, the answer is very simple. Look at how many products I have that changed, because I have to modify for all of them. So let's say that in this case, I'm going to create something slightly smaller. And only modified product 92. There is no product 92 in this database, which I happen to, at this point, know intimately. So let's see what's going to happen now. Now I have only a single document that was modified. So the answer at this point is that the cost of ETL in terms of network traffic is very simple. Whenever I need to write a document through ETL, we're going to make that request over the wire. If there are no writes that has to go over the network, there is no connectivity that I have to deal with. At the same time, if I have many writes, they would typically be batched into a single write to the server. Okay, I think in terms of loads on the server, probably not. I don't think that we will put a lot of load on the server, because even if you have 100 locations and you have 10 changes a second in each one of them, then that's only give you a maximum of 1,000 writes. And maximum of 1,000 writes, if they happen individually, Raven is not really going to notice. But because you're writing to many different servers, then there are going to be some batching going on, and 1,000 writes is not going to be 1,000 individual writes, but in batches, that's going to be much easier for us to handle. Okay, more questions. Okay. Guys, this is the time to ask questions. If you have any, please ask them now. If not, you're welcome to ask them at the in the mail list, or ping the support if you have something specific that you want to share privately. I'm going to wait another moment or two to give you a chance to ask questions. While we're waiting, the whole design of RavenDB has been meant to be really boring. It's, well, at least externally. Because the whole idea is that having to deal with a lot of the minutiae of how do I build distributed systems correctly and properly is decidedly non-trivial. And because of that, one of the design goals that we have is to be able to take on ourselves all of that. Things like doing multi-level synchronizations, making sure that everything works, distributed aggregation, stuff like that. This demo that I just showed with the product recommendations and do that in a distributed fashion, try to imagine how much it would be to try to do something like that using your own technology if you had to write it from scratch. Try to imagine using other stacks. And with RavenDB, I do that in a few minutes, and it's not really noticeable. And that's the key thing for us. And I think that at this point, there are no more questions. So thank you very much. I hope you enjoyed this, and goodbye.